last year with my internship with Uber. These are the folks involved in the paper. Raj and Lazaro are also here, so you can go talk to them. And yeah, so this is going to be a talk about the code transformation. So don't lose me yet. I know this is not the right session, but trust me, it's interesting. So yeah, so before I tell you about this language, I really, so this is done with Uber. I have really to tell you a bit about Uber to get you the context and the reasons that drove the design of this language in the first place. And so Uber is a pretty large software company. So it has over 4,000 engineers. And they collectively maintain roughly over 100 million lines of code. And this is spread across 7 or 8 programming languages that you can see here. Cool. And so, so as you can imagine, software development at this scale demands generally for automated code refactoring, rewriting tooling. And so what I mean by this is tools for finding finding opportunities and automating necessary large-scale changes. So to give you a very concrete example, Uber uses feature flag-driven development. So that essentially means every feature that's implemented in Uber is guarded by a flag. And so a flag is just a toggle, right, that triggers a particular behavior within Uber services. For instance, in the app, you can have this is dark mode flag that will activate dark mode. And so as time goes, and the experiments go, a lot of these flags can become stale. Right? Then what I mean here is flags that always become true or always become false. So you can think of it dark mode as permanently being on. And so if the code that's guarding this flag is not regularly cleaned, technical debt will start to build up. And what I mean here is you'll have this dynamically unreachable code because this method is now always true. So there's a lot of clutter in the code base. And it's not only just an else block. You'll have these this import statements that if everything needs to be simplified. And this is even more challenging if you think that these changes may propagate across multiple languages and code bases. And so how can we automate this sort of cleanup task? Sorry, my mic is. I apologize. Okay. Cool. Yeah. So how can we automate this sort of cleanup task? And so we looked into multiple solutions, and most modern code transformation tools and tool sets can be placed on this plane of language specificity and expressive power. And so at one end, we have these matched replaced languages for code transformation. They're language agnostic and very easy to use, but they've very limited expressiveness power. And then on the other end, you have these very powerful compiler frameworks that allow you to rewrite and transform code using extensive APIs based on simple information and so on. But so the problem with these is that they, so the other one I told you is most of them are easy to use but limited, and the other ones are very expressive but also complex and language specific. And that's a problem, especially if you want to automate something like feature flag cleanup across multiple code bases. And so that's why we proposed this language and tool set called PolyglotPiranha. It's just a lightweight polyglot code transformation language. And this language is, PolyglotPiranha is, everything in Piranha is a match replace rule. And the idea is that we extend the match replace paradigm in multiple ways to make it more expressive and usable for large scale changes. And so if you remember something from this talk, is that the idea, our core idea is that we can compose and combine multiple match replace rules in order to make them expressive. And everything in Piranha is a match replace rule. And we basically have 3 ways of composing and combining these match replace rules. And I'll go through each one of them with concrete examples. So the first one is composition within multiple matchers with a single rule. So if you see this code snippet here, let's say this is just a class with one unused private method and another used private method. And let's say for the sake of this example that we want to write a match replace rule for deleting unused private methods within like the Piranha language. And so what you can do is you can just like write a simple matcher using your favorite matching language of your choice. So this is using comping syntax. And the idea here is like these, what you see, like the colon and the brackets are basically templates. Like they can match like anything. So we're trying to match against a particular structure. So if you see here, like for this example, if you write this matcher, this is like the code you're going to select. So in this case, notice we are selecting the used and the unused private method. And like this is something you can do with other languages, not necessarily Piranha. But what's interesting now is like the goal here is like to just select and delete the unused private method. So what you can do is you can again compose and use another matcher in order to further constrain the code you're going to select. So in this case, we have like this where constraint here where you say, well, I only want to match that private method if the enclosing class, that's the enclosing clause we have there, only contains one usage of the identifier from above. So you see the name is whatever you selected in green here. And so if you notice here, this identifier, set dark mode, that we selected from there, is used 2 times within this class. So this is like heuristically, this is not an unused private method. And so like it will not be selected by Piranha because like the matchers are not satisfied. That makes sense. And so, yeah, so like this is like one way in which you can combine the matchers. And then if you just want to delete the code, you can just like match this and then replace with empty string. And that's like one of the core ideas. And so like now you might be thinking that, well, this sounds very approximate and heuristic, and that's true. The transformations that we have in our language are always only going to be sound if the rules you propose are sound. Anyway, so moving on, let me show you more features about our language. And so like the second core idea that we have is the context propagation and the controlled rule application of rules within particular scopes. And so I'll show you that with an example. So let's say this is again the example from the dark mode we saw earlier. So let's say we have like this class flags, and this is dark enabled is just a method that's always true. Dynamically, it's always going to return true. And we want to clean this up across the code base. So what you can do, like if you just like want to find and delete this method, you can just like, look for the method that's declared with the annotation dark mode, and you can just delete it. But then if you want to propagate this across your code base, like let's say this is also being used in another class, but like in Kotlin, so you know this declaration is in Java and the usage is in Kotlin. What you can do in Piranha is you can apply this method globally. You can say like apply another match replace rule using the context from the previous rule, but globally in this case. That means across the entire code base. So you see here like the method in the second rule is being taken, the context is being taken from the first rule that there. And so this will be instantiated at runtime as dark enabled. And that's like what the using clause is saying there. And so if you do that, you can propagate the change again. And this will replace the usage. But then if you want to keep on cleaning up the code, you can basically add more rules in order to further clean up your code. And so what you have here, you can chain another rule call. And so you have like this, in this case, I'm saying only apply within like the surrounding code context because we don't want to do this across the entire code base. And we can have like another rule for simplifying if statements. So you can see here, if true, then you can just replace this entire statement with a consequence. So you see there, if true, we can just like replace everything with whatever is inside the truth block. So everything else is deleted. And so like the idea, our idea in Piranha is that you can basically chain these match replace rules using scopes and context. So the first one is the global scope that I showed you, but you can also say, first apply the first rule within the entire code base, and then the second rule only within the context of the same file where the first one was triggered. And you can do that within the file, class, method, and then we have like this parent scope, which basically says only apply it around the context in which the first one was applied. And you can define your own. So we support many match replace rules and scopes. Cool. And so the third way in which we can combine match replace rules is using multiple languages. So what you saw here, the syntax that I show you is just like the combi semgrep syntax, but you can also use three-seater queries and regular expressions, whatever you want. But if you want to learn more about that, you really have to read the paper, because I don't have time to tell you about it right now. Because I wanted to show you how we use this language and how powerful it is. And so this PolyglotPiranha toolset is deployed and used in production at Uber. And so in the paper, we basically provide 3 case studies in which we use the language to build tooling. And so the first one is automated feature flag cleanup. And then we also have 2 migration tasks that we did. And our idea with this evaluation is just to show desirable properties of the language, like expressiveness, and effectiveness, etc. And so for this talk, I'm only going to focus on the first case study and on effectiveness and usefulness. And so in this case study, what we did, we basically built a tool based on the PolyglotPiranha toolset where, yeah, maybe that's going to work. Okay. Yeah, okay, cool. Yeah, so we built basically a tool. I think the mic's not picking up. It's okay. Yeah, so we built a tool on top of Piranha, which does feature flag cleanup, and we did this for our 2 code bases, two of our mono repos, Android and iOS. And these are pretty large code bases, as you see here. It's 7.5 million lines of Java plus Kotlin for Android, and 7.5 million lines of code for Swift. And we did this, the code is mostly open source, so if you want to learn more about how we did it, you can read the paper. But I want to tell you what exactly we did with this language. So this tool, basically what it does is it's a job that's running and basically produces PRs to delete flags that we think are stale. And so over the course of roughly 5 months, 6 months, Piranha produced 4,700 PRs. For cleanups, this shows you how many of them were for Android and for iOS. And so out of these roughly 5,000, 60% of them pass continuous integration tests. And so the reason we have this gap between, not all of them are passing CI, is because sometimes whenever you clean up a flag, the test suite, the semantic changes to the test suite, so tests start failing. And the developer has to commandeer the PR and adapt the test suite based on whatever their understanding of the flag is. And the other big reason for the tests for the PRs to fail CI is due to linters. So basically, Uber uses a lot of linters, and if you don't exactly follow the guidelines, the CI will not let you land your PR. And so roughly, then you can see at 2,600 PRs passing CI. And then we also send these PRs to developers to make sure that the flag is really stale, because we don't want to delete codes that shouldn't be deleted. And so that's why we have this gap of here, PRs that have not been accepted yet. And developers still have to review them in order to land the changes. So this gap is closed in the previous, in the last months, but this is the results we have in the paper. And so out of these PRs that have been merged, the ones, roughly 1,000 that have been merged, the tooling was basically able to automate most of the changes. 90% of the changes were automated by the tool, 90% that you can see here. And this is the chart shows you the total lines that were removed, and this is ordered by this is the ordered flags. And out of all these PRs that were produced, 76% did not require any user intervention. So that means the change was just accepted and the flag was cleaned up. And this distribution is very skewed, so you can see towards the end here. These are the user and the tool deleted flags. So here you can see in some cases the developer goes and deletes a lot of files and classes. So that's why you see how many lines deleted towards the end of the distribution here. Okay, so that's pretty much all I have. So we to give you an overview, it was this polyglot code transformation language. We have a tool which is open source, so you can look at it. The paper is there. And yeah, we have also an open source package for the tool and the artifact, so go check that out if you're interested. Thanks.
We have time for a few questions.
Hi, the tool looks very exciting. I had a question regarding the rules. Can we specify data flow rules as well, or is it only kind of syntactic? Hey, if this is found, do this. This is found, do this.
Yeah, so like this version of the tool, this is all syntax driven. So like the rules are only matching and replacing code.
So, okay.
So it's always syntax. You just like match and replace, but you can.
And can the rule specify context? Can I say, if find this function name and in that function something should be there?
So you can say find that function name, and then within that function you can do something.
Can I use the same function name within the function? So here, let me why beat around the bush. Let me ask the question straight. So if I have if I want to remove a recursive call, how will I remove it?
I see. Like that's. Oh, you mean like deleting an recursive function?
Yeah, I mean, see, you had a rule that said if it occurs in the class only once, but the recursive call maybe the same function is called directly or indirectly.
So like this is all an approximation. So you cannot specify that.
Oh, you cannot specify such.
No, because this is it's all about matching code. So like everything is a syntax matcher. And so like some things you cannot express because we don't understand semantics at all within the language. We're just like looking at the syntax. Yeah.
Okay, thanks.
So like that's not something you can do, at least for now.
Kind of a follow-up on that question. So for those cleanup rules that are like, syntactic approximations that you can clean up, who's writing these rules? Is it driven by developers or is it mostly people that work on PolyglotPiranha?
So like the rules for simplifying expressions like the if cleanup that I showed are already written, like someone wrote them and like that's provided within the core of the tool. Like someone has to write them, but generally only once. Now, if you want to do something very specific, like doing API migration, which is something you can do with the language, you still have to write them manually. Like someone has to write them. Yeah.
Thanks.
I would go through the paper and look at examples of multiple languages, but could you tell me if the code is, if it is calling a piece of code in another, so do you have interprocedural rule matching specifiable where I call code in a different language?
So you can, since everything is syntax driven, you can basically apply rules across languages. So you can pretty much propagate the context of the previous rule that was like called, like say in Java to Kotlin.
Okay.
So like, since that's the reason we did it in a syntactic way, because we wanted to be able to support many languages and allow them to interleave and propagate.
Okay, so
context.
the context would be basically dependent on the rule that you specify.
Yeah, the rule gives you the context.
Let's thank the speaker again.